Hello, this is Mark Werawath. I'm here to talk about software engineering productivity and software engineering economics. How do you forecast the time and effort for software development? This has been something that in the early days of software, was very difficult. Of course, we had very few metrics, very few data sets that we could use, and very little historical practice. So we eventually had to rely on people like Professor Barry Boehm, who wrote this amazing book on software engineering economics. He introduced us to the Kokomo estimation model, which I'll get into in a few moments here, asking fundamentally, at the essence of this book and the essence of this talk, how long does it take to write a line of code, right? How elastic is the effort time curve, meaning how many people will actually add value as you add them into the project versus at what point will they start subtracting value? So do 3 times the people give you 3 times the output, or is it something less? And what is that elasticity? How can you estimate it and forecast it ahead of time? And those types of questions, to some extent, are starting to be answered in this book, but unfortunately, this book is somewhere between 30 and 40 years old. The Kokomo model evolved into Kokomo 2 and a whole bunch of other models, and I'm sure you can research, after this talk is over. But fundamentally, if you're trying to understand software distributions for time and effort and proper teaming, this is a great historical place to start. As we all know, we have this agile versus waterfall debate. And I don't think it's much of a debate or a controversy. I think in general, agile brings a lot to the party in terms of tightening that loop between development and defect discovery and defect resolution. The tighter you can bring that loop in, you're going to basically improve productivity and reduce software development times and development effort. So tightening that up is everyone's goal. Waterfall did the opposite. It kind of stretched it, where agile tightens the loop and basically gives you all those benefits. Part of the problem, of course, with agile is you don't really know how many loops you're going to have to go through. How many sprints do you need to get to the finish line? And that's assuming you have a fixed finish line. If you have a variable finish line that says, well, we're going to cut it off when we meet some sort of, budget deficit, or we keep going until the customer says good enough for us. But that's very difficult to forecast in terms of how long will this project take to finish, right? So I don't think you get straight answers from Agile. If you do, please let me know. The basic equation, of course, that I want all project managers with linear thinking to think about is, what's the effort needed for the new features? Because you're adding new features into that software, but you're also fixing known bugs from the past, right? You can't live with some of these bugs in your new domain, or you just promised a certain number of bug fixes to your client base or your customer. You're going to be doing some testing. Most testing falls into new feature testing or regression testing. Both of them take time. In fact, typically regression takes longer than new features, because what you're doing with regression is you're making sure that the new features didn't fix any of the old features, didn't break any of the old features. So towards that end, regression is by its nature going to take longer unless you automate, unless you actually bring in some automatic regression testing or some sort of scripts that automate that process. What is the effort for building and integrating each load as it gets submitted into test? Because that effort is often overlooked. So it's not just coding, but the effort of building that code into a release package that includes release notes, that includes documentation, it includes basically every module being built, compiled, if you will, and put into a proper load package, right? Unfortunately, with every test, you're going to find bugs. So you're going to have to then factor in an effort for fixing the new bugs and for the testing and regression and new feature testing that goes with those new bugs. So again, a very iterative process that reminds us again of Agile. So what's nice about the sprint is that the next sprint can deal with the last sprint's bug issues and factor that into the kind of fixed planning window that each sprint represents, right? So for each load, if you will, you have requirements, you have inherited code, you have inherited architecture, you've got a dev environment, you've got fixes, you've got new features that go into a build process that includes a library, configuration management, release notes, and then ultimately goes out into integration and testing and other types of reviews. So This is kind of a high level picture, if you will, of how it should look. A lot of people prefer the V model, where coding is at the bottom apex, if you will. This is where basically you're going from the pre-coding to the post-coding phase, right? So on the upper left, you've got requirements gathering, systems analysis, software design, module design. All of these lead sequentially into your coding phase. Until that's done, you then get into unit testing, integration testing, system testing, and acceptance testing. So that's the V model, right? And of course, the big concept is, from concurrent engineering concept, the people downstream on the right-hand side of the V should be involved with the people doing the work on the left-hand side of the V. So the testers should be involved with your requirements people. They should not be divorced from each other. They should be hand in glove, working together, so that the requirements that you're writing are testable and the test scripts that you're writing are based on requirements. So there should be no surprises here. We're not going to be improvising. This is hopefully a rigorous, traceable process, right? So things to consider when you're doing your estimation, right? What is the quality and stability of the code base, right? What's the experience of the coders, the experience of the team with the code? The degree of embeddedness, is this standalone code or is it embedded and linking up with other pieces of code, right? What's the complexity and size of the code? What's your time constraints and resource constraints? Because when you're under time and resource constraints, things tend to break faster, right? Configuration management, how are things managed in terms of the check-in, check-out process, your librarian functions? Do you have proper configuration so that you're not fixing stuff you've already fixed, if you know what I mean? Writing code that was written before, but was somehow lost or misconfigured or somehow written over in your librarian function. Some ways to estimate software, some foundational elements of software, right? The number of features, the number of functions. The difference, of course, the function is, what you define up front as, the complexity of the requirements, whereas the features are kind of the output in terms of complexity of the code, right? So we make that distinction as, functions define features. Functions are requirements, features are embedded in the software, okay? The number of lines of code themselves. How many lines are you writing? And KLOC represents thousands of lines of code. And then we realized the line of code wasn't the same as another line of code. So then we went back to KELOC, which was thousands of assembly equivalent lines of code, okay? The number of expected defects, the defect discovery and resolution curves, which ideally converge upon each other and cross over. Historical data, how long has it taken you to do features like this in the past? And then, of course, expert opinion, the Delphi method, where you just basically say, how many days do you think this will take you to do, right? So the beauty of Delphi is that, first of all, you're triangulating on multiple, series of expert opinions, but over time, it's self-correcting. So even if you wind up being high or low, if you are tracking your actuals, you can track your actuals against those expert opinions and start to normalize and say, okay, this expert's usually 50% high, this expert's usually 20% low, and you can wind up kind of normalizing the data that way. So Kokomo, if you look at it, and the book goes into infinite detail, I can't afford to in this video, but basically looks at 3 different types of code: embedded, semi-detached, and organic, right? It looks at development time. It looks at product size and the time taken for all 3 categories. So if you look at development time in the first graph on the left-hand side, you see that the size doubling from 30 to 60,000 lines of code doesn't necessarily double the amount of time. You go from 14 months on the organic scale to something like 18 months on the organic scale. So doubling the size does not double the development time, right? Conversely, if you look at size and effort, you can come to similar conclusions there as well. So when doubling the size does not necessarily double the effort. So these curves are all embedded in the book. The book has all sorts of detailed examples and formula. Some of the formula get into such things as understanding the the various coefficients in his tables, the development times, the person's P calculation, the E for effort, right? So basically, again, he breaks it down by organic, semi-detached, and embedded. And he basically has the formula you see at the very bottom, which is a function of thousands of lines of code. And EAF is the factor calculated from the tables above. So again, this is very similar. The defect discovery curves that I mentioned before looks at basically the found fixed rates for the typical project and the more efficient project. In the typical project, there's a lag, a delay in resolution. You let defects accumulate and then you fix them later, which is bad practice and, frankly, does not tighten that loop the way I was talking about before. So what you get in that case in the upper curve is a discovery rate and a fixed rate. So the red and the green that never cross over, right? They never basically get to the point where you're reducing the defect backlog. On the bottom, where you're actually more efficiently dealing with defects, you're dealing with them in real time, you're dealing with them quickly, you're tightening that loop, right? What happens is the found rate gets crossed over by the fixed rate, and the fixed rate overwhelms the found rate, and you now have defects, the backlog is reduced, the defects are getting resolved, versus in the upper scenario, the defects have this quote unquote debt accumulation, right? And why do we do all this? Why do we care about finding software defects before a product ships? Well, the truth is it's much more expensive to find defects later in the process, right? So if you find a requirements defect, for example, in the upper red-hand curve, defects found via traditional acceptance testing, design defect found via traditional system testing, those are far more costly on the right-hand side over here than, for example, finding them during the green sections, which is, pair programming, which is fundamentally a form of inspection, continuous integration, test-driven development. These are early stage defect discoveries versus late stage, right? So again, if you tighten that cycle, you're finding the defects earlier, they're far, far cheaper to resolve and faster to resolve as well. So the key is, of course, to get your requirements analyzed for defects far sooner than you would have otherwise found in system testing. So the overall thinking here is in the new paradigm in the blue, what you're doing is finding discoveries, rates of discovery of defects much earlier in the process during the requirements and design phase versus in the testing and field testing phase where it's far, far more expensive. Significant rework would be required and you have an increase in cost. So the cost is much, much higher the later you discover your defects. So again, earlier discovery, tighter loop between testing and development. And basically this is a vote for your agile approach, which agile should solve most of those problems for you. So with that, I will call it a day and say, feel free to dive deeper into the Barry Bain book and the various COCOMO estimation models that have been since replaced with others, COCOMO 2 and other more sophisticated models, most of them available online.